Well, it's great to see the John CMSA Tsinghua Math Science Literature goes well. Thanks a great deal to Dan Fee, who managed it in the most excellent manner. And we are very happy that our students and faculties are benefiting a great deal by listening to these lectures. And it also good that we have both people from America and China in Tsinghua to give talks that we can learn from each other. Yeah, thank you, Dan.
Well, thank you, Yao, and thanks to Yao for starting this series many years ago. There are many wonderful lectures in this series, which are on the CMSA YouTube channel. So I recommend you find them there. And today we're very happy to have Nicolai Reshetikhin tell us about asymptotic representation theory. Call you.
Okay. Thank you. So I was considering various options what I can talk about, and I thought this is a great subject. I'll explain why. So when I was preparing it, I remembered that some time ago I asked Yuri Manin about his recollections of his young days. And he very politely refused to do this, but the way how he did it was very elegant. So he said that when we were young, we were looking to the future, and I still do this. So I couldn't say anything, but in this talk, I'll still be looking to the past a little bit. So it will start with an overview of some aspects of the asymptotic representation theory. And then there will be also some sort of look forward, some conjectures and questions. So what is not included in this talk is harmonic analysis on infinite groups, S infinity, U infinity. It's a beautiful subject. It's related to free probability, which will not be here as well. And the relation to random matrices will be only mentioned. And there are many other aspects that will not be here. Otherwise, it would be a few hours, not an hour and a half. So the idea of this branch of mathematics is to study large representations of large algebraic structures. And it can be done in two ways, somewhat similar to statistical mechanics. One can study various probability distributions on already infinite systems. That would be analogous to Gibbs measures in statistical mechanics. Or one can study the limits when finite dimensional objects become infinite dimensional or infinite objects. So that would be an analog of the thermodynamic limit in statistical mechanics. An example of such situation is when we take finite tensor product of finite dimensional vector spaces, for example, Cn to the power n, and we'll study the asymptotical behavior when both the dimension of Cn goes to infinity and the number of factors go to infinity. So that's a typical example. And now here is the scientific landscape that surrounding the asymptotic representation theory. Well, first of all, it's a representation theory. And the questions in asymptotic representation theory are mostly of probabilistic nature. So somewhat similar to statistical mechanics. So probability theory is very prominent. It has close relations to statistical mechanics, to functional analysis, to geometry, and to quantum theory. So again, in this talk, it will be very difficult to focus on everything, so I'll choose some subjects that sort of are most coherent. So let me start with reminding what a partition is. So if we have a non-negative integer, and if we split it into, say, L parts such that they form a decreasing sequence, all entries are non-negative, that's called a partition of N, and L is the length of the partition. That's a traditional terminology. So here's an example of the partition. We have lambda 1 equals 7, lambda 2 equals 5, and you can guess the partition of what it is. It's a partition of 14. So partitions are important because they are for many reasons, but in particular because they parameterize irreducible representations of the general linear group and of the group of permutations, the symmetric group. So, so we will be taking the limits when both n small and n capital go to infinity. So in particular, we'll look into representation theory of S infinity. So now one of the important measures on in representation theory is the Plancherel measure. So in the most general setting, it can be phrased like this. Suppose that A is an associative algebra, V is a finite dimensional representation of A. We can decompose V into the direct sum of indecomposable components. So here Ni is the multiplicity of Vi in V. And then on this space of on the set of indecomposable components of V, we have a natural probability measure. It's the multiplicity of this component, the dimension, its dimension, divided by the total dimension of V. Naturally, these numbers are non-negative, and that's a probability distribution because it sums up to 1. So the original version is when V is a left regular representation of the symmetric group, and we decompose it into irreducibles. In this case, every irreducible appears in the multiplicity equal to the dimension of this irreducible, and the Plancherel measure on the set of partitions of N is just this. So it's the dimension of the irreducible parameterized by lambda squared divided over the size of the group. That's number of elements. That's n factorial. So naturally, it can be regarded as a measure on partitions of n. So then the usual version of the infinite group of permutations is the inductive limit of finite permutation groups. In other words, these are all finite permutations of the infinite set 1, 2, 3, and so on. So the Plancherel measure on each individual Sn can be so-called Poissonized. So we can consider the measure on all partitions given by this formula. Theta is some positive parameter, so it's one parametric measure of one parametric family of measures. So it's one parametric family of measures on the irreducible components of group algebra of S infinity. Okay, so these are the basic facts we just wanted to mention. So now a brief history of asymptotic representation theory with many omissions. So the story goes back to works of Nicolai Reshetikhin, Sergei Kerov, and then I think Benjamin Logan and Lawrence Shepp. From 1977, they independently came up with the following very nice result. if we look at the Plancherel measure and take the limit n goes to infinity, then the measure concentrates in the vicinity of a certain deterministic shape, which can be described as follows. So it's more convenient to turn the usual, say the usual Young diagram would be something here. That's how it's usually written, not everywhere, but so if we introduce coordinates u and v by this formula, then we basically turn this diagram upside down. And so this is a picture of the Young diagram for Sn. And then as n goes to infinity in Plancherel measure, after rescaling of the Young diagram by the square root of n, so it converges in probability to this continuous Young diagram, the limit shape, which is given by this formula. So by this formula. So you should think of this like in the following way. If you consider very large n, then most of the Young diagrams will be in a small vicinity of this limit shape, and this size is square root 2 square root of n, 2 square root of n, 2 square root of n. So the question about the limit shape was solved back then, but then the question about fluctuations remained open. And it was Borodin, Okunkov, and Alshansky who kind of sorted out this question. So it's best to describe the answer in terms of so-called Frobenius coordinates, and actually in terms of Frobenius Kerov coordinates. So Frobenius parameterization of a partition is the following. So we have the diagonal in this Young diagram. These are the blue squares. And Frobenius coordinates is just the number of boxes from the blue square to the right. That's P1, and then P2, P3, and so on. And then also the number of boxes to the left. That's Q1, Q2, and so on. So in this example, we have 2P, 2Q, and that's an example of the Young diagram. And Frobenius Kerov coordinates, these are the coordinates of the centers of these segments. So to the left of the blue squares, it's the left tilted segments. To the right of blue squares, it's the right tilted segments. All right, so fluctuations of this random Young diagram distributed according to the Plancherel measure for large n, they can be described as follows. So consider the Poissonization of the Plancherel measure just for convenience, and then the Poissonized correlation functions, which is the following. It's the probability that these points x1, xs, they are part of the Frobenius Kerov coordinates of some partition lambda. So the main result of that paper is that these probabilities are given by a very simple formula. It's the determinant of certain matrix. And the matrix is given by the so-called kernel K which is certain combination of Bessel functions. For now, it's not important because actually all the computations in this domain of mathematics are quite heavy. So this is the most important fact, that it is a determinant. Now, the next step, we can consider the Schur-Weil duality and the asymptotical behavior of these representations. So it's a story about asymptotic of Schur-Weil duality. So consider Cn small n to the power n capital. On this space, we have the action of the symmetric group by permutations of factors, and the diagonal action of GLN by simultaneous action on these vector spaces. So the Schur-Weil duality between GLN and Sn acting on this space is the following theorem. These two groups, the action of these two groups centralize each other in this representation. In other words, the decomposition of this module over Sn cross GLN is multiplicity free. In other words, we have this decomposition, and because V is an irreducible GLN module, its height should not be greater than n. And so the Young diagrams that appear in this decomposition, they must fit into this strip of width n. Now, I should mention that this is really a special situation. It's related to some interesting Markov processes, but we will discuss this at the very end. So one can ask many questions about this representation space and these groups. So one of the questions was asked by Kerov, and he gave a positive answer to this, is how the Plancherel measure on this Plancherel measure in the generalized sense on GLN irreducible components behave in the limit as n goes to infinity. So the probability, so it's a, you can think of this as follows. It's the probability measure on Young diagrams with n boxes that fit into the strip of width n, and this probability measure is given by this formula. So what he discovered is that as n goes to infinity, this probability measure on such Young diagrams weakly converges to the probability measure given by the eigenvalues of Hermitian matrix. So it's just the radial part of the distribution on Hermitian matrices, Gaussian distribution on Hermitian matrices. So that was the first observation of that kind. The proof is elementary. You just use the formula for dimensions. You use the Weil formula for the dimension of V lambda and the Hooke length formula for the dimension of irreducible dimension of the symmetric module of the symmetric group, and then use the Stirling formula to compute the limit as n goes to infinity. And so in this case, the Plancherel measure concentrates in the neighborhood of zero partition, and the average size of fluctuations is the square root of n. And so the weak convergence means that if you take the expectation value of a test function h with respect to this discrete measure, then as n goes to infinity, it converges to the expectation value of h with respect to the continuous measure. So that was 1986. And then in 1993, Philippe Bien, he came up with another very natural result, describing the asymptotical behavior when both n capital and n small go to infinity. And we're talking about the Plancherel distribution of irreducible GLN components in Cn to the n. Now, just heuristically, if you think about the Young diagram of length n, of height m, with n capital boxes, then you kind of expect that the number of boxes should be of the order n small squared in order to have something sensible. What Bian did is he used approximate factorization of characters and concentration theorems for characters of Sn for large n to prove that in this limit, the same probability measure, the Plancherel measure on this large tensor product, converges to another measure that's, I shouldn't have said, yeah, it's the Young diagram lambda converges in probability to a certain limit shape that is described earlier. So both n goes to infinity, and the ratio n over the square root of n capital is fixed. So then if c equals 0, we go back to the Vershik, Kerov, Logan, Shepp results. If c is between 0 and 1, it's one limit shape. I'll show the picture. If c equals 1, then it's a very special case. It's the point of phase transition. And when c is greater than 1, there's this new piece of the limit shape, the straight line. So here h, you see some strange function. And so here is the picture. So when c equals 0, you can recognize the Vershik, Kerov, Logan, Shepp limit shape. By the way, Vershik, Kerov, the order of names is because in Cyrillic, V goes before K. So it's a translation from Cyrillic, but the order became opposite. So if c equals 1, it's still kind of smooth curve, but if c less than 1, the curve has this straight line, and then it becomes smooth. So there is some special phenomenon here. So this straight line, it disappears. It disappears when c equals 1. So this is what I said, that c equals 1 is the phase transition. So then you can ask, what are the fluctuations in this case? And that was done later. Remember that Borodin, Okounkov, and Alshansky computed fluctuations around the limit shape for the Plancherel measure in 1999. And this is a later result. So Borodin and Alshansky, they computed fluctuations around this Bien limit shape. And again, the fluctuations are determinantal. So the probability of, if we fix x1, xk, then the probability that it's a subset of Frobenius-Kerov coordinates for some partition lambda as n goes to infinity it's the determinant of certain kernel that can be expressed in terms of Hermite polynomials. And again, you can look to the reference and find all the formulae. If I'll write this formula here, it doesn't say anything. The most important feature is that it's a determinant. Okay, so two important things to notice is that we have a phase transition when c equals 1, when n is exactly square root of n, and correlation functions are determinants. Physicists would say that, okay, correlation functions are determinants means that the system is the system of free fermions in some sense. And this is actually true. I'll mention why it's true. But I want to kind of point out that I think there is some problem that hasn't been well studied. It's just a remark that if you take Cn capital to the power n capital, zero-weight subspace, if you decompose it into GLN irreducibles, then you will have a zero-weight subspace here, which is isomorphic to W lambda itself. So we go back to the decomposition of the left regular representation of the symmetric group. That has been studied. But if we say that we have n here, then and we have some weight mu here, then I think this is an open problem. But you know, if you know what I'm talking about, you can think in this direction. But I have no time to explain the details. So now there is a beautiful part of this in this area. It's the study of the longest increasing subsequence in a random permutation. So here is the brief history of this subject. So there is this beautiful combinatorial fact, Robinson-Shenstedt-Knuth algorithm. It's a bijective correspondence between permutations of n objects and pairs of Young tableaus of the same shape. So if you read about just the construction of this correspondence, it's very easy to find all the information on the internet and ChatGPT, in Google, how this bijective correspondence looks like, how to work with it. But the interesting fact, well, algebraically it's easy to remember it, because what it means that there is an isomorphism between the group ring of the symmetric group, where the basis is just given by group elements, by permutations. And the direct sum of endomorphisms of W lambda. So this is just the decomposition of the left regular representation into irreducibles. And this RSK algorithm, it gives you a linear map from kind of an isomorphism between these two different but isomorphic spaces, which brings one basis to another basis. So standard tableaus, they form a basis in the irreducible representation of the symmetric group. And so this RSK correspondent gives the well-known algebraic fact. And so if you have a uniform distribution on the symmetric group, it gives the, on the right side, it corresponds to the Plancherel distribution on the on partitions. And then it turns out that the length of the longest increasing subsequence in a partition, consider it as a random variable. It corresponds to the first entry of the Young diagram in the Plancherel distribution. Again, consider it as a random variable. So what follows immediately from this result by Vershik, Kerov, and Logan, Shepp is that for large n, the expected value of the first entry of the partition, of random partition, is about 2 square root of n. And as a consequence, the length of the longest increasing subsequence in a random partition taken with respect to the uniform distribution random permutation taken with respect to the uniform distribution on random permutations, it's also of the order 2 square root of n. And then after this came celebrated result of Baek, Dave, and Johansson, who observed that if you take the difference between the between the length of the longest increasing subsequence of a permutation minus its expected value for large n, divide by n to the 1/6, then it converges to the Tracy-Widom distribution for random matrices. So it's a rather non-trivial observation, which used the Riemann-Hilbert problem technique, and then they improved this result in 1999, also proving similar result for the second eigenvalue. But about the same time, Okounkov somehow explained why this is happening. So let's consider random Hermitian matrices with Gaussian distribution. We have seen those matrices already in the result by Kerov about the Schur-Weil duality for large number of factors. But but here the size of the matrix will go to infinity. So let's E1, E2, E3 be ordered eigenvalues of a Hermitian n by n matrix, random with Gaussian distribution, and define these random variables for I plus 1, 2, 3. They are also ordered. So then for a partition lambda 1, lambda 2, lambda 3 with Plancherel distribution, define x's by this formula. They're also ordered. And then the theorem that Okounkov proved in this paper is that as n goes to infinity, the joint distribution of x1, xk is identical to the joint distribution of y1, yk for any fixed k. So in other words, kind of loosely speaking, random partitions distributed with respect to the Plancherel distribution are equivalent in this sense to Hermitian matrices distributed with respect to Gaussian distribution. And then came another paper clarifying this remarkable result by Baek, Dave, and Johansson, by paper by Borodin, Okounkov, and Alshansky. I already mentioned that paper, so I'm mentioning it again. So the result is that it extends the results of Baek, Dave, and Johansson to all entries of the partition and describes the correlation functions between these points that are coordinates of partitions in terms of kernels K and the structure of these kernels agree with the Tracy-Widom distribution, and this result reproduces the these previous results by Dave and Johansson, except without going into a great deal of kind of Riemann-Hilbert problem, simply by computing certain multiple integrals using the steepest descent method. Okay, so that was the story about the Schur-Weil duality. So now Schur-Weil duality and random partitions and Hermitian matrices. So now there is a story about Schur functions. So in some sense, this is about characters of GLN as n goes to infinity. So in 2003, with Andrei, we had a paper where we studied random plane partitions, Schur processes, and the limit shape in this situation. And the technique was using vertex operators, essentially some vertex operators for GL infinity to compute local correlation functions. So random plane partitions can be considered as just simply monotonic arrangements of piles of cubes, monotonic piles of cubes in a corner of an infinite room. So something that's written here, it's monotonic in every direction. So then if your room is a little bit more complicated with the with the walls that change the pattern, so and your piles of cubes are still monotonic, so then the statistics of such cubes can be described by random skew plane part. So these are the random skew plane partitions, and one should consider skew Schur processes where you have the where skew Schur functions play the role, sort of in a way slightly different from the previous way. So so both of these results are secretly related to dimer models in statistical mechanics. And just one can look at the special case of such piles of cubes. Namely, we can make a cut. We can cut through the middle over here, and consider only the left part, and also make a restriction on how large this left part can be. So then we have the following. So imagine that this is the wall of this infinite room, semi-infinite now. This is the floor of this room, and then you have piles of boxes, but some of the boxes are cut by the diagonal over here. So, and then you define the sum of all such piles with a length. This size should be n. And then you take the product over all slices like this, some weight xi, and then the number of boxes in the slice pi. So it's just basically the partition function counting the configurations of boxes like this. And it turns out that this function is exactly the Schur function. In order to prove this, you just have to notice that these piles, they are identical to so-called Gilfan-Settling patterns that describe the chains of embeddings of GLN. And as a consequence, they describe a basis in every irreducible GLN module. And this basis is a weight basis. So the diagonal matrices acts diagonally on this basis. And that's the reason why this expression that has nothing to do with, at first look, that has nothing to do with GLN, actually is the character of the irreducible representation of GLN, the character of V lambda. So there is a way to rephrase such counting in terms of dimer models on the hexagonal lattice. So if this is a hexagonal lattice, dimers can be placed on edges in such a way that, so this is the lattice, in such a way that two such dimers cannot touch each other, and they should cover all vertices of the lattice. So it's a very nice story, and again, I want to cover a certain amount of material, so that's why I cannot go into the details. But the importance of this analogy is that the dimer models, partition functions of dimer models, can be expressed in terms of Pfaffians, and in this case, in terms of determinants. And this is so-called Castellan solution to dimer models. And that allows to study thermodynamic limit. And what we want to study in this case, we want to study the limit when n goes to infinity, and the weights, the arguments of the character, and the label of the irreducible representation, the partition lambda, they behave in this way. So here rho is some function, rho and sigma are functions on the unit interval. What kind of functions? It's a separate story. They actually can be distributions, but let's assume that they are nice, smooth functions. So here's a conjecture, which I think it's true, but again, I have never seen any kind of substantial. I think it's open. So if you take the logarithm of this partition function, then as n goes to infinity, it behaves like this: n squared times the maximum over the so-called height functions. Well, the height function is just as n goes to infinity, piles become continuous kind of surfaces over a triangle in the R2 plane, and this surface is called height function. So the conjecture is that we should maximize the entropy plus this contribution from the weights with certain boundary conditions determined by sigma, by the limit of lambda. And the entropy is given by the same formula as the entropy in Damer models and in tilings of, so it's also related to tilings of the triangular lattice, which is dual to the hexagonal lattice. And you can see that you can think of this pile of cubes as a flat projection where we have and these piles, they will be in bijection with tilings of the triangular lattice by rhombi, which are dual to the dimers on the hexagonal lattice. So, so this surface tension, it goes back to the work by Kohn, Kenyon, and Propp. And I wrote work in progress just because I'm curious whether this is true or not. And I hope if I'll have time to do this, but if anyone wants to solve this problem, it's fine. So, okay. So this is about characters of GLN as n goes to infinity. They have this funny asymptotic. So far we were focusing on GLN and the symmetric group for large n. So what about other simple Lie algebras? So let G be a simple finite dimensional Lie algebra, classical Lie algebra, say orthogonal or symplectic, or any of the exceptional Lie algebras. And let's take any irreducible finite dimensional G module with the highest weight lambda, integral dominant highest weight. Let's take nth tensor power of such representation. So then if we decompose it into irreducibles, every irreducible will come with some multiplicity. The domain where these irreducibles will occur with non-zero multiplicity will be some area in the dual space to the Cartan subalgebra, some polygon. So on this set, we have the Plancherel measure, again, given by the, so the total dimension of the space is just the dimension of V nu to the power n, and then to every partition we assign the probability given by the product of the multiplicity times the dimension of this irreducible component. So first question is, what is the asymptotical behavior of this multiplicity? Generally, these multiplicities are very hard to compute. But, you know, usually these computations simplify in two opposite extremes, for very small representations and for very large representations, and for different reasons. So now let's assume that n goes to infinity. We rescale the highest weight in such a way that lambda over n is some finite vector in H dual, n goes to infinity, and then the same Philippe Bien computed the asymptotical behavior of the multiplicity in this particular way. So he showed that if S is regular and strictly inside of this domain, then the multiplicity behaves as n to the power minus r over 2, then the determinant of some matrix, and then all these factors. So here the function S is, I mean, it's all related to large deviation theory and probability theory. So this function S, physicists would call it the action function, probabilists would call it the large deviation function. So whatever it is, it's we should minimize this combination with respect to xi and with respect to y, and the extreme, the minimum is exactly the s of xi. So anyway, so here I explained all the notations, I think. So k is given by this formula. Delta is the denominator of the Weil character formula. So f of x is log of the character of evaluated at e to the x, and b is the inverse to the symmetrized Cartan matrix. Okay, so this is the result of Bien. So he obtained these results by computing the asymptotic of the integral of characters and using the orthogonality of characters. So then in 2004, Tati and Zeldich computed the asymptotical behavior of the Plancherel measure itself. So what they found is that if you rescale lambda by the square root of n for the Plancherel measure, then the measure becomes this continuous measure. That should be, so xi is identically equal to a, sorry for these notations. So rho is the half of the sum of positive roots, and we have the weak convergence of the Plancherel measure to the probability measure given by this formula. And again, h is a test function on the Cartan. So so for any test function, we have the convergence of the sum to this integral. Okay, so this is for the Plancherel measure. So now let's look at some other measures, and so there is a natural physics motivation why to consider character measures. So let's consider n atoms, quantum atoms, which can be spin up or spin down, which means that to each atom we assign a two-dimensional space of states, and then the total space of states is the nth tensor power. So sigma iz is the projection of the spin to the z-axis. It's a physics terminology. So what we have, the essence of this is that we have the density matrix, which is given by this exponent, and our partition function is the normalizing factor for the density matrix, so that its trace will be 1, and it can be computed in two ways. On the one hand, we can say that it's the character of the two-dimensional representation to the power n. On the other hand, we can compute it by decomposing the this tensor product of irreducibles for SL2 into irreducible subrepresentations. And as a result, we have a deformation of the Plancherel measure. So you can see that Plancherel measure corresponds to t equals 0. In this case, the character becomes the dimension, and we go back to the Plancherel measure. But of course, if we want to study the physics of these atoms in a very strong magnetic field where we can neglect all other interactions, then we just have to study the quantum statistics of these atoms for these Boson weights, for this density matrix. And in other words, we have to study the statistics of invariant tensors with respect to this distribution. So here T is h over k times the temperature, and you can see that if h is very large, we neglect all the other interactions. If t is very large, we keep our parameter t finite. So it really describes some real physics for high temperatures and strong magnetic fields. Okay, but now go back to mathematics. So let's re-examine the same problem of large n limit of Plancherel measures for large tensor products of irreducibles for simple Lie algebras. So again, G is a simple Lie algebra. V lambda, we denote irreducible representation with the highest weight lambda. So then V nu to the n decomposes into irreducible components. But now we will study not the Plancherel measure, but the character measure on these irreducible components, where T is some positive vector, some vector in the real principal Weil chamber. So, for example, so here's the principal Weil chamber for SL3. It has the interior blue, and it has walls here, and it has the corner. So the corner obviously corresponds to t equals 0. So this interior corresponds to t being regular. And here, t is irregular. Regular means that the centralizer of t, if you consider coadjoint action, the centralizer is the whole Cartan subgroup in G. If it's irregular, then the centralizer is bigger than Cartan. And then if it's SLN, then you have the whole stratification of the boundary of the principal Weil chamber by the size of the stabilizer of vectors on this stratum. Okay, so when T is regular and strictly inside the principal Weil chamber, so then plus some other restrictions, but I will mention them later. So then the probability converges to just Gaussian distribution. It's not the same as in the Plancherel case, when it converges to some kind of radial part of the distribution of Hermitian matrices. So again, we have weak convergence. Eta is the Legendre image of T for the corresponding large deviation rate function. And so again, we have the convergence in probability. If we take a test function on R small is now the rank of the simple Lie algebra, then the expectation value of the test function with respect to the discrete measure converges as n goes to infinity to the expectation value with respect to the continuous limit. So this is our result with Postnova. that goes back to 2018. Pre-COVID, then was COVID, many unpublished results, and then the recent kind of clarification of this result is a short joint paper with Postnova and with Serganova, which is the following. Suppose that now T is on the wall of the principal Weil chamber. Well, in this case, T defines a Lie subalgebra in G with the root system delta 0, with the condition that the killing form, the scalar product between T and alpha, is 0 for all alphas in this subroot system delta 0. So G0 into G, it's a root embedding, so the root systems are also embedded. Let R0 be the rank of G0. Then, I mean, it's obvious that if T is 0, if we are in this corner, that's T equals 0, then G0 is the whole Lie algebra G. If T is regular, if we are inside of the principal Weil chamber, then there is no G0. G0 is 0. So then, so for when T is on the wall, we can decompose the roots into two subsets. This is a positive root system, positive part of the root system delta 0 for the Lie subalgebra G0, and the complementary set is just some collection of positive roots for any root from delta 1 plus the scalar product of T with alpha is positive. And then we can restrict irreducible G module V nu to the Lie subalgebra G0. Then it decomposes into the direct sum of G0 irreducibles with some multiplicities. So the dimension of this space W is the multiplicity of V mu G0 in V nu. And then define this number. It's a funny number, but it is what it is. So in the numerator, we have the trace of e to the t over this space W. So e to the t acts trivially on this space, and it acts non-trivially on this space. So we take the trace of e to the t over this space, the dimension of the G0 irreducible, then the Casimir, and then the dimension of G0 and the character of V nu. So the theorem is that when T is on the wall of the principal Weil chamber, then our probability distribution, the character distribution, converges weakly to this product of continuous measures. So here we have the, I'll just include these differentials. So now we assume that lambda has this form. So there's this eta that's, you can think of this as the limit shape. And then the convergence of the probability measure to this probabilities means that we study the fluctuations. So A and B, they describe fluctuations. So one fluctuations are along the wall of the Weil chamber, and the other fluctuation is inside of the Weil chamber. So you can see that this is what you expect from the Plancherel measure, and this is what you expect from the regular distribution. So now it's the product of both. It's interesting that they're not correlated in this case. So then here's the description of the ingredients of this distribution. So kappa is involved in the rescaling. K1 is just the matrix of second derivative of the character. The eta is the Legendre transform of T. Rho 0 is the half of the sum of positive roots for G0. This is the killing form for G0. And this is the inverse of the symmetrized Cartan matrix for G0. And as I said, one factor describes the fluctuations on the wall, that's Plancherel measure, and then it should be vice versa. That's Plancherel, and this Gaussian, and this is Plancherel. So in particular, if we are in the origin, then we only have the Plancherel fluctuations. And if we are in the bulk, then there are no Plancherel, we only have Gaussian. Maybe it was correct. So sorry, it's very late here. So it's a homework to see which one is which. But one of them is along the wall, the other is going in the bulk. All right, so we more or less concluded. So it was, the first story was about GLN and SN, both. We studied these things for large N. The second story was the representations of G. And so one can continue these two affine Kac-Moody algebras. Very interesting story, but very unfinished and actually not started. Except there is one paper by Eugen Fagin on this subject, but nothing else. So, but now we know that groups and Lie groups, it's a beautiful subject, but we can go beyond this to very natural structures, to Hopf algebras, to tensor categories. And let's start with how this can be generalized to supergroups. So in 1987, Berele and Regev, they constructed a version of Schur-Weil duality for the supergroup GL and M. Well, kind of roughly speaking, you can think of this as the linear transformations of the super vector space. Of course, all this should be done more precisely, but super vector space as a vector space is just Z2 graded space, nothing more than this. But if you will try to construct tensor category from these vector spaces with tensor multiplication, then the braiding morphism, the permutation of two factors, will be sensitive to which vectors you're permuting. And if the vector, so these are the even vectors, here x equals 0, here x equals 1. So if you're permuting odd vectors, you will gain -1. If you're permuting even with even or even with odd, you don't gain anything. So as vector spaces, they're just Z2 graded, but if you take the category of these Z2 graded vector spaces, it's a totally different tensor category. So, but this is exactly what we want to do. We want to take the tensor product, tensor power of this vector representation of the general linear supergroup. So then this is what these two gentlemen observed, that this tensor power decomposes in the following way. Instead of the having restriction on the height of the Young diagram, as in the usual Schur-Weil duality, in this case, the supergroup GLNM and SN, they still centralize each other. So the multiplicity is still free. But the representations that occur here, they should fit into the hook of the vertical size n and horizontal size m. So these are the representations that occur there. And now the Plancherel measure, in order to have it, one has to take super dimensions of V lambda and super dimensions everywhere. So fortunately, this is the representations of the symmetric group are still the same. So these are the usual vector spaces, the usual dimensions. But here you should take super dimension and super dimension of the Z2 graded space. It's the dimension of V0 minus the dimension of V1. So it's not even obvious that these numbers will be positive. Clearly, at least the denominator will be positive if n is greater than m. So again, you have the kind of probabilistic problem here as well. So, but this is totally open problem. What happens as n goes to infinity, it's not clear. There are some partial results by Berele and Regev, and then later by Regev about the asymptotical behavior of sort of these objects. But this question about the distribution is open. And the same goes to characters. Okay, so this is about supergroups. And then for quantum groups, very little is done. I think there's only one paper that's by Lachowska, Postnova, myself, and Solovyov from 2024. And it's about the following. Let's take UQSL2 at the root of unity. And let's take Lustig's integral form with divided powers. So then, if you take the smallest irreducible, non-trivial irreducible representation of UQSL2, that's two-dimensional, take it to the power n, then it decomposes. So now the algebra is not semi-simple. There will be indecomposable components. And fortunately, the structure is nice here. So this tensor power decomposes into the tensor product of tilting modules. So what we did is we investigated both Plancherel and character measures. And there's an interesting connection to lattice path. So if you just take SL2, the usual SL2, then there is a well-known decomposition of the two-dimensional representation of SL2 and irreducible with the highest weight L. So, and so as a result, if you will keep multiplying C2 to the n, you decompose, and then you multiply again by C2 using this rule. Then multiplicities can be computed as the number of lattice paths. So these are the lattice paths. So they go like this, from L to L minus 1 to L plus 1, and then L plus 2, L minus 2. So this is where it can go, and lattice path, they go like this. So this is the picture of lattice path. And this is the kind of what happens if you take the SL2 to the n, and we'll be studying the statistics of representations there. But what happens for UQ-SL2 is very interesting, because some of the decompositions, they have multiplicity 2. The red arrows here, they actually have the multiplicity 2, and then some representations, they so some of the decompositions, they can jump back by L, so rather complicated lattice path, and still these multiplicities of tilting is still equal to the number of lattice paths. Okay, so again, it's a technical work, impossible to explain in a few minutes, but I think I explained the main result. So there is a limit shape, there is a convergence in probability, everything that we discussed before holds for UQ-SL2. For UQ-SL3, there are some preliminary results, but it's quite complicated. Quite complicated because the structure of tilting models is quite complicated. So, so now the next step is one can go from UQ-SL2 to arbitrary braided tensor categories or tensor categories. So one can ask various questions. For example, one can ask the question about statistics of projective models in a tensor category. There is a series of papers by Colombier, Tsinghua, Ostrik, Tubinauer, which study these questions. So some of these over the final characteristic, very interesting kind of numerological results. So finally, one can ask what happens when we take tensor products of affine quantum groups. In particular, if you take the Yangian and we'll take its representations. So why it's back to the future? Because it goes back to the study of quantum spin chains, where the space of states are the lambda 1, but now it's the representation of affine quantum group, quantum affine. So what happens as n goes to infinity? It's a whole special universe, and as a byproduct, some time ago with Anatoly Kirillov, we got some combinatorial formulae for Koska polynomials over certain q to the number of it's a long but very nice story. So what happens when lambda and mu go to infinity and q go to 1? There must be some interesting limit here, but this is totally unknown. So I'm finishing a little earlier, but I assume that maybe there will be some questions.
Thank you, Kolya, for a wonderful and comprehensive talk.